works. Now the audio should be on. Is that correct? So you can hear me. Okay.
Hello, welcome everybody to this TNO webinar for PCSI partners on self-healing for cybersecurity. 1 second, I'm going to fix the camera. Because the camera was focusing on Sharna. So after this small mishap, we're very happy that you found the time to join us for 1 hour, and I hope it will be interesting and stimulating to you. My name is Shari Finner. I'm responsible for our project portfolio on cyber resilient infrastructures, and I'm here with my colleagues Bart Gijssen and Swarna Kumaswamy Das. And before we dive into the content of this webinar, let me introduce a few house rules. First of all, we've decided not to prevent you as participants from speaking and video sharing, as we are with a reasonably small crowd, but please do keep your microphone muted until at least we reach the question and answer moment in the end. And there will be a bit more room for discussion. Also, we're recording this webinar, so if you are switching on your camera or speaking, be aware that you're being recorded. And should you have any questions or any comments that you do not want to share plenary or that you think of later, feel free to email us or me or my colleagues. What we'll discuss today is how to deal with the ever-growing challenge of keeping our infrastructures secure, our IT infrastructures. And I'll first give a short introduction. And after that, Bart will dive into the details of our work, and Swarna will wrap up before we move to the question and answer session. And I think the problem we're trying to address here is quite known to everybody who made it to this webinar. Enisa said already in 2017, the cybersecurity community is still far from striking the balance between defenders and attackers. And that was long ago. And what happened since then, it's only increased. We have a new geopolitical situation. All the headlines we're seeing are getting more and more. And of course, this rat race of attackers and defenders is exactly also the reason why all of us who work together in the Partnership for Cybersecurity Innovation in the PCSI. And in the PCSI already in 2019, 6 years ago, an idea arose to take inspiration from other rat races. Where else do these kinds of rat races between attackers and defenders take place? And one of the analogies that they came up with was the challenge of the body in the rat race, in the constantly being under attack by viruses, by bacteria, parasites, everything. So how do living beings stay alive, and how do they thrive while constantly being under attack? So a team of PCSI people formed. There was, for instance, Paul Samuel, who was here in the meeting, back then still at Rabobank, also Rogier Remer from Achmea and some TNO colleagues, and also both ABN AMRO and ING participated in this project, and they were very enthusiastic about using the outcomes of that PCSI project. And today, in 2025, we're still talking about self-healing for cybersecurity and autonomous cyber resilience, so I guess they did something well. Now, if we look at the rat race of attackers and defenders in biology, what can we learn from that? In biology, we've got the human immune system that keeps us safe. And there's a few things that the immune system is very good at. For instance, one concept is that cells are disposable, so they can be replaced. There's many of them. There's negative selection, so whenever there's something compromised, something infected or mutated that might evolve into cancer, it will get killed on purpose. So we're using the disposability concept there. And if the first response is not enough, killing a cell or killing several hundreds of cells, then the immune system's response gets escalated to higher levels. So it's a multi-layered response that can be used to not only mitigate detected attacks, but also undetected threats where compromises or new bacteria, new viruses haven't been detected yet. And if we want to use this concept for our IT systems, Well, we're not so far yet. Usually our IT system, our IT infrastructures are protected by security operations centers centrally. And what we are saying is if we want to learn from the human immune system, is that you need to take this concept of disposability and negative selection that I've just briefly introduced and put that into our ICT infrastructure so that your applications can regenerate themselves. So that will be an autonomous cyber resilience part at the bottom that would need to work together with the Security Operations Center. So the Security Operations Center would be kind of the brains in the biological analogy, and the autonomous cyber resilience in the infrastructure would be a more decentralized thing. And this reminds us of a concept of thinking fast and slow in human decision making, where you've got a fast decisions. They're simple, they're intuitive, but they're kind of, well, stupid, not simple. Whereas if you have decision making in the brain, in the neocortex, then you can do thorough analysis and reasoning. You can use centralized information processing, but the process is a bit slower. So the idea with our autonomous cyber resilience is that these systems work together. So maybe one disclaimer: self-healing for cybersecurity will not solve all our problems. It will be needing to work together with the Security Operations Center, and it will only give the defender a bit more control about how to defend, how much to defend, when, how much energy to spend on it, and so on. But it will not solve all our problems, and the rat race will persist, but hopefully the defenders will stay a bit more ahead. Now, this was a bit, of the introduction of the general concept. It's not only fiction, it's actually that work has been done on this also within the PCSI, earlier called SRP, Shared Research Program. And my colleague Bart will now take you through the journey that has happened of the technical work within the Shared Research Program and the PCSI.
Thank you, Sharon. I guess this works. Thanks again, and as Shari already mentioned, we have some of the guests in our audience which were involved in the earlier stages of the work of self-healing that we did together with our PCSI partner, so I was very happy to see that. And there's also quite some people that are relatively new to self-healing and other concepts that are highly related to the self-healing work that we've done within the PCSI, as well as beyond the PCSI. What I will be talking about in the next few slides is doing a very brief recap of the work on self-healing for cybersecurity version 1. And then also pinpoint to a particular review that's been done by ABN AMRO within the PCSI, just to make sure that not every problem is solved if we have the version 1 of self-healing for cybersecurity. There were quite some, say, open issues that still were challenging and are still challenging today. In the PCSI, we not only went into the topic of self-healing for cybersecurity, which is mainly focused on trying to get ourselves rid of, say, viruses and other infections and contaminations, but we also addressed the topic of we also only want to have authorized access to particular parts of ICTM structures, so trying to do zero trust. These were all done within the PCSI and the predecessor of the PCSI, but we also continued this line of work. And as I will explain, it's become quite a fundamental aspect of the cybersecurity work that TNO is currently doing. In that sense, I will go into cybersecurity version 2, and I'll also address some of the challenges that we're currently are trying to tackle. Now here you're looking at a slightly over-complex diagram. This might be a bit overwhelming, but in fact this is a very, very simplified version of all of the actions which are going on within the human body and within the human immune system. So you have to think that back in 2021, and actually we started on this work in 2018 already, so well before the Corona pandemic. We put together several microbiologists, immunologists, as well as cybersecurity experts. We were challenged with the fact of trying to make sense out of, okay, what kind of defensive mechanisms are there in the human immune system and how can we transfer those to the IT domain? Now, I will not go into all the details here, but there's a lot of very important aspects which you can learn from the human immune system. And in particular, if you start to look at the differences between normal IT practices, such as if it ain't broken, don't fix it, and trying to transfer that into a system which is very dynamic. And there are three key aspects which are very relevant in regards to self-healing. If you look at the human immune system, first property which is very relevant is the property of disposability. No human cell in isolation can break the system. And this is one aspect which is being, used or abused, depending on how you look at it, by the immune system. It may kill at will, so to say, as long as it's trying to keep the overview of, okay, try to kill more non-self than self human body systems. The second part, which is quite relevant in the human immune system, is that it works in a highly decentralized way. There's no central part in the brain which has an overview of everything that goes on in the body in order to signal where to act. And this is opposed to much of the current cybersecurity operations, where we kind of presume that there is some kind of a theme or some kind of an overview where we try to figure out, okay, this is the overall picture, and now we need to fix this part. So that's another quite fundamental difference between the human body and our current IT systems. And the third one is the level of adaptiveness. What we're always having some problems with is if you target a particular attack, are we actually targeting the attack or are we making things worse? So a proportional approach is very important. And this is where the human immune system provides some inspiration. If you look at the cooperation between the innate human immune system and the adaptive human immune system, which is only invoked if the innate human immune system cannot solve the problem by itself. So looking at those, fundamental insights that we gained from the human immune system, we try to compose our version 1 of self-healing for cybersecurity. In the analogy, human body cells should be resembled with something like what we at first called microservices, but application containers. Typically, within an infrastructure, you would have thousands or tens of thousands of containers running all kinds of application workloads, probably redundant versions of those. So that's a lot of stuff which is actually doing the actual work within your IT environment. Next to each and every of those applications, we deployed something what we call the lymphocyte software. It's kind of a control loop which keeps track of the runtime of the application. So is there any, expired application or human body cell death needed? Is there any anomaly going on in the application? And if so, then it can act. The way it can act is that we implemented a so-called host Docker daemon proxy, such that all of those lymphocytes, which are in the separate pods that we have in our infrastructure, and they can call on the Docker daemon to kill a particular container. Now we configured this whole infrastructure of microservices or container platforms in such a way that once an application is killed, Kubernetes will restart the entire pod. So it will restart the application as well as the lymphocyte logic and make sure that the application is restored to its original version. Now, once you have such kind of a regeneration mechanism, you can start to add more monitoring tools. And in SelfHealing for Cybersecurity version 1, we implemented the cloud-native tool called Falco. Falco captures all of the system calls that the application makes to the platform. For example, whether or not you are downloading files or whatever other kind of action that is being done from the application. And based on all of those system calls, it can analyze that and try to figure out whether or not some anomaly is going on, which requires some action by the lymphocyte. The lymphocyte collects all of this information, and then it can decide based on all of the information on whether or not it is time to regenerate the application, so to kill it and make sure that Kubernetes restarts the application again. Once you have that, you can add further, say, adaptiveness to the system as a whole, because the Falco system as well as the lymphocyte are quite, say, rule-based. So as Shari mentioned, the fast-thinking control loops in our self-healing system. And then you can start to add the more slow-thinking control loops, which, for example, based on machine learning algorithms or whatever, can modify all of those rules that are running within Falco to detect certain kind of anomalies, or to adjust the lymphocyte control loop that's out there. So here's an example of how the thinking fast and thinking slow are intertwined within the self-healing for cybersecurity concept. Just to give you an example, the software components that were needed in order to implement this self-healing concept were all programmed in Python. And here you see a small code snippet. I will not go into any of the details, which allows the host Docker daemon to call on the actual Docker daemon and to make sure that a certain application gets killed. And then Kubernetes will restart that same application from a fresh image again, which is supposed to be not infected. In order to experiment with this whole mechanism of self-healing, we implemented a very, very simple use case, which consists of a Nginx web server and a PHP backend, just for demonstration purposes. We used, as I mentioned before, Falco to capture whether or not, say, large file downloads are going on, and we used the PHP backend to signal if any, say, false login and usernames were used, signal that towards the lymphocyte node. And then we would, say, take kind of an attacker use case, and the attacker would undertake two types of attacks. First off, it will do a brute force attack on the web server. So it would try to figure out all kinds of combinations of username passwords. Of course, those were then captured by the PHP backend, and they were sent to the lymphocyte, and the lymphocyte would decide to regenerate the application if at least, say, 5 or 10 false usernames and password combinations were used, because that might be an indication of compromise of the application web server. Also, once the attacker would do a very large or an unusual large file download, that might be an indication that some information is being extracted in an unexpected way. So that would be detected by Falco, and that would be triggering an anomaly, which would immediately stop the file download from the web server application. Now, these were very, very simple use cases just for us to experiment with how would this work. And then we asked our PCSI partners to reflect on, say, the work that was done until that point in time. So in September of 2021, ABN AMRO took the challenge, and their status team installed the self-healing for cybersecurity software in their development environment. They experimented with that and they did a quite extensive code review. I'll just present you the highlights of the critiques that came up from this review, and there were 5 of them. The first one was, the way that you're doing regeneration of an application container is quite harsh. If that application container is actually doing some kind of work, or if it's in process of exchanging information, that data might get lost and work might be, say, compromised simply by killing it at will. There was no way of interacting between what the application was doing and the regeneration part. So that's quite harsh. Secondly, keeping in the analogy with the human immune system, this way of regeneration might introduce something called like a cytokine storm. You might actually DDoS your own system by doing way too many regenerations. If you in some way attacked anomalies falsely, then this might simply DDoS your own application. So have you looked at that kind of security aspects of it? And the third critique was actually the most important. It was at ABN AMRO at that point in time. They did use Docker and Kubernetes, but they used them within the Azure Kubernetes service. So they used Microsoft's cloud service in order to run their Kubernetes workloads. Now, Microsoft doesn't allow you to talk directly to the execution platform, which is the Docker platform. It doesn't allow you to send a kill instruct for a particular application. You will have to abide to clean Kubernetes APIs in order to make the whole self-healing concept work. So our mechanism was a bit too over-engineered in the sense that we directly targeted the Docker daemon for this. And they said, if you abide to the clean Kubernetes APIs, then you get other benefits too. You can not only use, say, the self-healing mechanism of Kubernetes, but you could also use the role-based admission control mechanism, which is also by default installed in AKS. So that was the first hint that we got on trying to combine, say, access control with the self-healing part. In order to make sure that if we would put effort into, say, extending self-healing for cybersecurity version 1 by adhering to clean Kubernetes APIs, we asked, together with ABN AMRO, we asked some guys at Microsoft, in particular AKS experts, on whether or not this might work. So if we would refactor all of the self-healing software, making sure that it's adhering to Kubernetes APIs, could we run that within AKS? And their answer was like, yeah, clear. No further modifications needed. You can simply deploy and run. This will work. And the final critique that we received is actually not a critique, but it kind of emerged in the discussions that we had together with ABN AMRO along these lines in this review. And they said, well, there's one other thing that we'd like to add on the feature list for self-healing, because you're now regenerating an application container from the same container image over and over again. But if you change that, and if you allow the system to also use, say, patched versions of the application container, then combining this mechanism of updating your container images with the self-healing mechanism kind of provides you with an autonomous way of doing software patching, because you're regenerating anyway. So if you regenerate from patched versions, you get the improvement that you don't have to stick with the same container image for a longer time, and you can do DevSecOps by the box. Now, the implications of those critiques were that the first 2 remarks actually narrowed down the applicability of self-healing for cybersecurity to more, say, stateless containers. And as well as they should have kind of a forgiving SLA. So you shouldn't use self-healing mechanisms for workloads which are, say, very critical to your system. Then regeneration might be a bit too harsh. As I mentioned, the third critique was kind of fundamental. It prevented self-healing to be deployed within an AKS production environment, so we had to solve that anyway. And then say that the fourth remark that we had is, okay, you should not only use your own logging mechanisms, but you should adhere to logging mechanisms which are native to Azure Kubernetes services. So you should do some work on, you can only use those kind of logs which are available from systems like Prometheus or other kind of logging systems, and not directly go into systems like Falco and do syslogging all over the place. So, and then the last part was simply a suggestion for further improvement of self-healing. Having said so, and I'm making kind of a jump now from September 2021 to say April 2023, when Chino continued this work to start working on self-healing for cybersecurity version 2. And it was particularly targeting on making sure that we would adhere to Kubernetes native APIs. We would use cloud native tools and logging. And then our student, which was quite of a great inventor, he also added much more extensibility of the concept. So at that point in time, self-healing for cybersecurity 1 was kind of a closed loop control, relatively static, and he made it extensible by making sure that you could do a rule-based system and that you could reconfigure the rules on the fly without having to restart any of the self-healing mechanisms. And then the final point that we asked this graduate student to look at is to allow for integration of self-healing with NIST's Zero Trust architecture. Now here's what self-healing for cybersecurity version 2 more or less looks like. So the diagram that you see here presents a Kubernetes cluster and two pods, a pod X and a pod Y on top of that. And within each of those pods, an application is running. Now, the way that Kubernetes self-healing works is that from the cluster, it sends probes, so a readiness probe or a liveliness probe, towards the application, and the application will respond with, I'm okay. If it doesn't receive an okay, then the Kubernetes cluster will presume that the application has in some way blocked or has gotten contaminated or impossible to respond, and it will restart the application. Now, the fundamental trick in self-healing for cybersecurity 2 is that we did kind of a man in the middle for this. So we created the same lymphocyte software, but then it captures the liveliness probes and forwards them to the applications. If everything's okay, it will forward the okay back to the Kubernetes cluster. If not, if for some reason the lymphocyte decides that it should not be running, so the application should be killed, then it will simply withhold sending back the okay on a startup or a liveliness probe, and Kubernetes will restart the application container. So this is the way that you can very simply adhere to the Kubernetes APIs and try to intervene in this in order to make sure that your self-healing property gets in there. Now, once you have that, you can then start to add all kinds of logic, like you can introduce a metrics processor, which takes inputs from the application and then computes whether or not there's some anomaly going on and then send an alert to the lymphocyte. The lymphocyte can then, based on certain kind of rules, specify whether or not, or what it should do with it. So to give you an example of these kind of rules, the rules all work based on a triple of you get some trigger, then you check whether a particular rule is satisfied. So there's one certain condition which might get satisfied. And if so, then it will perform an action. Here you see a very small example of this, where in terms of if server errors occur, then you can, for example, decrease the timer in order to do regeneration faster than you would have if no errors would have occurred. In version 1, the regeneration was kind of black and white. Either you regenerate or you don't. These rule-based systems in version 2 are much more granular. You can specify whether or not you should regenerate, but you can also specify to do it a little earlier than you were supposed to do. And this is compliant to more or less, if you are talking about anomaly detection, there's in most cases not a black and white detected anomaly. And if there's an anomaly, you're not entirely sure whether it's malicious, yes or no. So it's kind of more probabilistic. This rule-based system in version 2 makes it, say, more in that context, and you can specify better that, okay, maybe I don't need to regenerate immediately, but at least faster than I thought I had. And this is, say, where the idea of a threat level comes in. So the lymphocytes keep track of certain kind of threat level, which is not on or off, but it can be a more granular stepping of threat levels. And if the threat level exceeds some threshold, then it will start to take action. It can then also do proportionally stronger actions based on the amount of threat that it's accumulating. Also, it's capable to exchange its threat level to its neighbors. So if some threat level for a particular application is getting higher and higher, it might inform, say, the backend which is connected to it by saying, okay, something fishy is going on here. And this can be included in the decision for the other applications too, to start their self-healing activity. As I mentioned, this is kind of a illustration also of where the thinking fast and thinking slow comes in, because from the Kubernetes cluster, we can also reconfigure the file. So the rules that we have, as I showed on the previous slide, are just YAML rules which you can modify, and then in real time, it will take into account the new set of rules. That's the kind of thinking slow loop that you can introduce with self-healing for cybersecurity version 2. And that's where the extensibility of the whole mechanism plays an important role. Then finally, not built into self-healing for cybersecurity version 2, but on our list to do to extend is our, say, preparations to make sure that you can enhance even further alerting on cloud-native systems and using logs within cloud-native systems, such as log processors or tracing processors, in addition to the metrics processor that we currently implemented in the version 2. Also, on the top of the diagram, you see that it's possible to introduce something called a service mesh proxy. So far, I've been talking about a system which simply allows the application to do traffic in and out, so to interact with all of the other applications within the infrastructure. But typically, you may also want to put a service mesh proxy into there. And if you have such kind of a thing, then you can do yet another self-healing action. You can, for example, pause all of the communication coming in or out of the application, which is slightly less harsh than simply killing the application. Also, this service mesh provides you with another option to do authorization control. So only admitting authorized requests coming into the application. And here's where the link between self-healing and zero trust lies. So let me take the step. As I mentioned, between the review on self-healing for cybersecurity version 1 and the work that we did on self-healing version 2, there's a gap of, say, about a year and a half. This is where what we did in between. Within the PCSI, in November 2021, a explore phase was started in order to figure out, okay, what can we do with zero trust, and what are the challenges that are still remaining in order to make sure that we evolve to infrastructures which are zero trust based. We did 2 explore phases where, amongst others, we did interviews with departments within the PCSI partners. And in the end, we kind of found the missing puzzle piece. And this is what we then call the zero trust orchestrator. I will go into that in the next slide. Then in the next phases, we try to do a proof of concept in order to build pieces of this zero trust orchestrator. And we did that together with some of our liaison partners, one of them Axiomatics, which helped out tremendously here. So let's zoom into this zero trust orchestration. What is that? In the interviews, we learned that there's different kind of access control rules, depending on whether you interview, say, the risk management people, or whether you have a procurement officer or a legal officer. They talk to you in their own business language in what they want to happen within their IT infrastructure and what should not happen in terms of authorizations. And this kind of a mingle-mush between, say, what someone from the procurement department will want you to allow employees to do, and what the legal officers will want you to allow. Also, if you look at the implementation side of authorization control, we learned that, for example, ASML was very into trying to use OPA, the Open Policy Agent, to do container authorization. Others were more looking at XACML as a standard for doing so. And then, of course, you also have the legacy systems like a SharePoint, which comes equipped with its complete own conditional access rules. And then you have SAP, which has their own access control rules and settings that you can make. So both from the demand side or the specification side, as well as from the technical implementation side, there's multiple options that you all have to tie together in order to come up with one, say, universal way of doing access control in your infrastructure. And here's where we saw the need for a zero trust orchestration. Zero trust orchestration would do something like being an interface towards the business side, trying to translate all of the access control and authorization rules that they specify into some kind of an abstract language. And then if you have that those rules in an abstract language, you will want to translate those to the implementation side. And whether or not that's OPA or a SAP business warehouse, doesn't matter. You simply have to translate that. So that's the key function of a zero trust orchestrator. But doing so, then you also encounter yet other challenges that you have to face. What if, for example, a procurement officer wants you to allow a certain employee to access some files, where the legal officer says, no way, only under those conditions? So you have to be able to have some function like detect conflicts in authorizations that can be set. Also, the paradigm of zero trust is never trust, always verify. What does always mean? How frequent is always? And is it actually always, or are there any limits to that? And then the last type of questions that we had were more on the implementation side, like if you implement this within the cloud, then what kind of other problems would you run into? And if we would like to use software-defined networks, can we make some mechanism where those abstract authorization rules get implemented all the way down into networks where you can do with yourself, software-defined networks can create those rules and enforce them. Those were, say, several particular cases that we looked into. And as I mentioned, we got tremendous help from Axiomatics to figure out, in particular, the translation part. They already had some great solutions for that. And together with them, we did some more experiments. And the results from those experiments in the pilot phases for Zero Trust, it kind of proved that all of our Zero Trust orchestration use cases that we had defined were a bit too ambitious. We were a bit ahead of, say, what can be technically achieved in the short term. So, and then in the meantime, of course, as I already explained, we get, say, the interaction between self-healing and Zero Trust, which we were working on. So there was a lot of things going on here. Now, here's a brief recap of, say, the activities that were done within the PCSI. And it shows you the timeline of where we got. Now, at TNO, we became quite interested and more convinced of the fact that self-healing is a very important aspect of future cybersecurity mechanisms. And we also started to do some work outside of the PCSI consortium. Even we were asked to prepare a National Growth Fund proposal called Autonomous Cyber Resilience. Unfortunately, our government decided somewhere beginning of last year not to fund any fourth round National Growth Fund proposals. But this did not stop TNO to continue on the way of further exploring the opportunities that self-healing and the integration with Zero Trust might offer. We started to recall it, rephrase it a bit in terms of autonomous cyber resilience, which is, in our view, say, the ultimate, say, process of where cybersecurity technology will go through. We started projects including the self-healing by design, as well as a early research program on cybersecurity by design. So in those projects, and here I'll just very briefly touch upon those because this is a real work in progress at this point in time. We took the opportunity to start working on a version 3 of self-healing for cybersecurity, in which we investigate questions like, okay, we program most of the software now in Python, but probably Rust or Go or some other system level programming language would be much better to do the thinking fast loop. And we also wanted to further improve self-healing in terms of the interaction with cloud native tools and logging systems. I'll not go into the details for this. If you'd like to learn more, please feel free to email us. We'd be more than happy to talk about this. And the last thing that I'd like to mention is that we also start to do some work on self-healing for non-stateless, so for stateful applications, as well as applications that are that do not have forgiving surface level agreements. From this, we learned quite some interesting points, and I guess we learned enough just to be able to start building a next version of self-healing, which is also applicable to, say, the more stateful applications and non-forgiving applications. And with this, I think I've come at the end of the development of the work that we've done in the past few years. And I'd like to hand the floor to Swarna to wrap up with the conclusions.
Yes. Thank you, Bart, for giving us a very nice recap and background. Also, of course, talking about the human immune system, what gave us the inspiration from TNO, but also the PCSI partners, formerly right from 2018 coming forward. So I would like to just conclude everything after what Bart has given us a background on trying to say that what we have been working on in this self-healing version 2.0 is really a completion of the lymphocyte software, in particular, trying to make it also compliant, like Bart already mentioned, to look at Kubernetes, the liveliness probing for one example. In addition, we have also laid the foundation in the version 2.0 to be able to add newer features, and also the feedback that we received from ABN AMRO. I will just come back to that in just a moment. And how this can be extended further to different use cases, but also how we try to customize this solution. Finally, of course, the SelfHealing version 2.0 is also available on as an open source software, and we've added the link, but you're welcome to reach out if you have more questions or interested in this. Finally, we also worked on a use case using the self-healing software, which Bart just showed in the previous slide as a topic. The demo is also available, which we can discuss further. Finally, also taking inspiration from the Zero Trust project of PCSI for inspiration in terms of looking at combining things with self-healing for better improvements in terms of access control or for authorization, for example. Looking at the feedback which we received from ABN AMRO in 2021, if I remember correctly, just to see how we have worked towards this in the version 2.0 and beyond. The first most important point which was mentioned was how do we gracefully regenerate these containers? Because if it's a stateless application, it's still can be regenerated, but when you look at stateful applications, this harsh regeneration will have other implications. How are we going to deal with this? We have started taking steps towards this, but I will show you that in a new version, we want to look at how this can be done in a better way, or in different applications, looking at stateful application, how can we still apply while ensuring the impacts of it is minimized by thinking of ways to regenerate in a way that we can still continue the mission objectives, for example. The second point, which was mentioned, how do you look at the self-healing if it's being attacked, if it assumes it's like a DDoS? So how can we prevent this sort of situation that the system is assuming that continuous regeneration would cause problems? This, I must say, as I've put a point here, that we are still investigating, and then we are still thinking of ways, how do we also add in the next version. Finally, looking at the compliance with the native Kubernetes API, this we have implemented in the latest version. We are also looking at ways to integrate self-healing with Zero Trust for access control. And this, we have started to prepare some possible directions to move, and it would be good also to have more discussions. If you all have any comments or something, or if you would like to discuss, we are very much interested to hear. Finally, looking at Azure native tooling, for example, event and log analytics. This has been prepared and implemented in the second version. And also we are trying to make more improvements in looking at other tooling instead of only the metrics aggregate. Looking at integration with DevSecOps, like, for example, if we have updated patched versions for regeneration, this is a very good idea, but we are still investigating how we can actually implement this. Looking at self-healing in other infrastructure, we are also working on the internal project, like Bart already showed in the previous picture. How do we look at these design principles? What kind of inspirations can we take for other infrastructures? And we are preparing some principles on this, which can provide some guidelines. This can help us also to implement newer updated versions, for example, when we're trying to use Zero Trust. We have also started investigating how to use self-healing in PLCs. This is a completely different infrastructure while compared to containerized cloud-native infrastructure. This is still under investigation, and we ourselves are quite curious to see what the outcomes would be and how to use these principles or what learnings can be there that we can make improvements in general for a newer version, for example, version 3. And finally, we are also working on looking at zero trust, but that's a slightly different domain in terms of manufacturing. It's Industry 4.0, but again, this is still under development. Finally, when we want to look at version 3.0, like Bart said, we have started working on this, but what are some of the ideas that we are already looking into or would like to look into? Using the first important one would be stateful applications. The second one was we haven't yet run it in an AKS environment. This would be really good to do in collaboration, perhaps with the PCSI partners, if we are able to run this, and then that would be a chance for us to look at what learnings we have. We have been working it from the TNO side, but then if we have a chance to do it with collaboration with the PCSI partners, it would also provide all of us some new learnings. Yeah, I already mentioned this about the integrations. Also to look at how we can look at self-healing response actions when we have scenarios when the authentication or the authorization are being attacked, or there is an attack scenario. Considering this, what type of self-healing actions can provide a good response. We are also working on an initial design that's still a conceptual design for architecture for the version 3.0, where we also would like to think of ways to integrate sticks. And finally, I would like to welcome you all. If you have more ideas, to reach out and have a brainstorm or collaborate, most welcome to do that. And I think that closes this finally. Yes. Any questions or reflections? Yeah. Oh yeah.
Hi, Swana. Hi.
Hi, Rob.
Yeah. I have a question. One of the things that I didn't saw in your presentation, I think, was generative AI. And you would think that would also enable a digital immune system, reading loggings and then advising to do the next best action. Is that something that is with a reason out of scope of your project?
It's a very good question that you have raised, Rob. I think we have been discussing on things of how to include AI as well, but then it's still quite complex. Or maybe Bart, you want to add something to that? It's definitely an important point on how to include AI, but at the moment we have still kept it out of scope. Or maybe.
Yeah, maybe to add on this. If you look at the thinking fast and thinking slow, then what we have been focusing on so far is on the thinking fast. So the mechanism that can make decisions, for example, if an active file download is in progress, make sure that it immediately captures that one and kills it. The thinking slow loop allows you much more to do, say, augmentations of the system and further improvements. So more elaborate data analysis of what the best action will be, or how to take away the cause of what's behind an attack. There we see much more reason to get into generative AI or any other type of AI, agentic AI solution. At this point in time, we'd like to keep those two separate in the sense that it provides you with absolute control. And also in terms of explainable AI, it's at this point in time not far enough to make sure that any of the actions that are being taken are actually explainable and as one of, I think it was ABN AMRO at one of the starting points, which pointed to, okay, so how are you going to do with auditability of the system? Because you're taking autonomous actions and decisions. Someone is accountable for this. Once we put AI into the mix, at this point in time, it seems one step too early.
I can understand it from different perspectives, that you prefer business rules instead of running an AI model. Last question, there's something a digital immune system cannot do, and that is deception, at least to my understanding. Is that also something worth exploring? So let's say it's harder to attack an environment when you are able to generate 10 environments that are very relatable but not contain the business sensitive information.
Yeah, so very interesting topic. This has been on the table too, and
Okay.
as you mentioned, immunologists and biologists that were involved in this have indeed explained that deception is not part of nature, apart from camouflage kind of things. Indeed, this is one of the interesting complements by, for example, I guess in the same kind of way as zero trust relates to self-healing, I think deception or providing honeypots or whatever kind of deception way that you would have in mind would indeed make sense in the bigger mix of the cyber defense layers that you want to have. Yet one other, just to take away the floor for that one, is to look at swarm behavior also. So if you look at the immune system, of course, it's a single system, which is typically very well comparable to, say, an organization's IT infrastructure. But if you look at, say, a whole sector of a lot of organizations, then you would have to look more at, say, population level healing mechanisms like multi-homing, swarm behavior, and the like. Those have been addressed, but I'm quite keen to make sure that those have not been, say, investigated in detail yet, but they're very inspiring ideas. Yeah.
Thank you for the information.
So I would add, if you have a concrete idea or use case where we could do that, we're very happy to explore together with you.
Yeah, well,
also, on the AI part, I wanted to add something. Of course, you've got the auditability, accountability, all of these things of the AI reasoning, which was preventing it from being applied right now, right? But at the same time, we're having early research projects where we are investigating the possibilities, and we're very aware that we need to connect the thinking fast and thinking slow one way or the other. The question is how fast, but I want to nuance that we are looking into it, but it's very carefully.
Something about the
Yeah, we recently visited the AI UK event in London, organized by the Alan Turing Institute. Shrana and me were there. And it turns out that our expertise is quite complementary, just because we have been looking so much into the technical realizations of this thinking fast, the local decentralized responses. We have already figured that out, and they looked more at the reasoning with large amounts of data, with deep learning, reinforcement learning, where I think TNO has a good position there, but there are other parties in the world that we can collaborate with to get that connection going. Did you want to add something? Okay, thanks for your questions. Any other questions in the chat or? Hi, Paul.
Yes. Hi, I have one question. Yeah, very nice to see what has happened because I left the project in 2018 or 19, I believe. I have a question about the probes that you are using, because at the moment I only see a liveliness probe and a startup probe. But if an application is compromised, yeah, if I would compromise an application, I would still allow it to send the liveliness probe. So what do you do to detect malicious behavior that's intended by a criminal?
Yeah, so the liveliness probe and the activeness probe of Kubernetes are very simple mechanisms to do what they call self-healing. And what we are adding with our self-healing for cybersecurity mechanisms is just what you are mentioning, right? So you want to have other types of information into the system which allow you to, say, restart a container. And this is where I think our mechanism works very well in combination with the Kubernetes self-healing system. But the self-healing system from Kubernetes is slightly too simple, and we're trying to build in, say, a way in order to make sure that you can take into account anomalies which are detected by other systems. This is actually the crux, I guess, of the addition that we made. Okay, does that answer your question, Paul?
Yeah, sure, it does. Thanks.
Any further questions? Good to see you, Paul, by the way, indeed. One of the founding fathers of all of our self-healing work. Any other questions? If not, as Swana already mentioned, feel free to reach out to us afterwards. We've just given a very brief recap of what we've been doing. There's much more work actually that's gone on here. And we're on the road towards autonomous cyber resilience as TNO, and we'd really like to share all these new developments that are going on at TNO, but also at other partners within the PCSI and other partners in the world, like the Alan Turing Institute. So thank you for now, and hope to see you and talk to you soon.
Thank you.